Hey guys, today we're going to be looking at vectors. This is going to be the first step in using motion in two dimensions, is understanding how to deal with vectors in two dimensions. So the first thing you need to know is that vectors must include both magnitude and direction. When you add them together, you must use the tip-to-tail method. So looking over here, you can see that this vector, this is considered the tail, and the point of the arrow is considered the tip. So when we put these two vectors together, we have a tail by itself, a point of an arrow touching a tail, and then the point of the arrow by itself. We always want to use tip-to-tail method. Using other diagrams, it's possible to find the correct magnitude, so the correct numerical value, but you will not have the correct direction as your final answer. That's why the tip-to-tail method is so important. So if we look at these three examples, the very top example, we have 3 meters per second to the right and another 2 meters per second to the right. Using tip-to-tail method, this is a total of 5 meters per second to the right or positive. Both of those indicate direction. The second one, we have our first arrow starting here because that's where we have a tail that is not near the point of an arrow, going 2 meters per second to the left or negative 2 meters per second, and then 3 meters per second to the right. Since these are in opposite directions, we're actually going to be subtracting them. So our total vector quantity is a positive 1 meter per second or 1 meter per second to the right. So the second example is very similar. The only difference is we have the purple arrow drawn first. Notice how this tail is by itself, and then we have a point of an arrow and a tail at the same location here. That's tip-to-tail method. So you go 3 meters per second to the right first, then 2 meters per second to the left. The total final answer is again positive 1 meter per second or 1 meter per second to the right. Vectors are very, very useful in terms of combining speeds of multiple items. Airplanes are a perfect example. If you've ever been in an airplane, you may notice that the trip to a location is a different amount of time as your trip home. This is due to having to combine the speed of the plane with the surroundings of the plane, or the wind that the plane is traveling in. If the plane is traveling north 80 kilometers per second, and there is a northward wind at 2 kilometers per second, the plane is actually traveling 82 kilometers per second. If that same plane is traveling south 80 kilometers per second with the same 2 kilometer per second northward wind, it's like the plane is only traveling 78 kilometers per second. If you are a bicyclist or a runner or someone who likes to canoe on a river, you know the idea or understand the idea of working with or against the wind or the current. If you are working with the current or with the wind, your run seems a lot easier because it's blowing in the same direction that you're traveling. If you're working against the current or against the wind, it feels like you have to put forth a lot more effort because the wind is actually acting as the source of friction to slow you down. That's what vectors essentially allow us to calculate. So what if the arrows aren't parallel? Consider this next example. If a plane is traveling north at 80 kilometers per second, and there is a crosswind of 60 kilometers per second, how does this change how we set the diagram up? Instead of simply adding or subtracting our vectors, we have to combine them a little bit differently. Over here, I'm going to draw a diagram. We have a northward wind of 80 kilometers per second, and we have a crosswind of 60 kilometers per second. Now, it doesn't tell us which direction the crosswind goes. The crosswind has to be coming in at an angle to that northward direction. We're going to use perpendicular because it makes it a little bit easier. So I'm going to add an arrow in this direction, and that's our 60 kilometer per second crosswind. So instead of simply adding or subtracting these vectors, since they're no longer in the same two directions, up and down or left and right, we actually have to find this component of its motion. We have to calculate the hypotenuse. In order to do this, we have to use Pythagorean theorem. So we know a squared plus b squared equals c squared. We know that we have a length of 80 and a length of 60. 80 squared is 6,400. 60 squared is 3,600. Our total is 10,000 equals c squared When we square root both sides, c is 100 kilometers per second. So even though we're traveling 80 kilometers per second, that crosswind allows us to travel a faster speed because we're no longer going in a straight northward line. We're now traveling northeastern based on this diagram over here. So here's an example practice problem. A weather station releases a balloon that rises at a constant 15 meters per second, but there is a wind blowing 6.5 meters per second towards the west. What is the magnitude and direction of the velocity of the balloon? First step is draw it. So we have our 15 meters per second north, and then it says 6.5 meters per second towards the west. The west is to the left. So I'm going to draw 6.5 meters per second, and we are solving for this green dotted line. We're solving for the hypotenuse. So we have to use trig again. We're going to use Pythagorean theorem to solve for the hypotenuse. And we have 15 squared plus 6.5 squared equals c squared. That's 225 plus 38.44 equals c squared. When we add those up, we have 263.44 equals c squared. And then square root both sides, and c is 16.2 meters per second. So we're really traveling a speed of 16.2 meters per second because of that 6.5 meter per second crosswind. Alright, so now we want to solve for the direction, and we're actually going to look for this angle right here. So if I write SOHCAHTOA to remind us what we're looking at, we have the adjacent leg and we have the opposite leg. So we are going to use tangent. So I have tan theta is opposite 6.5 over adjacent 15. Tan theta 0.433. Now since I don't have this theta, but I do have this number, I need to get rid of this tangent. So I'm going to inverse tan both sides to cross off those tangents, and I'm left with theta equals tan to the minus 1 of 0.433, and theta is 23.4 degrees. So we're traveling technically northwest at a 23.4 degree angle. One more practice problem. A boat is traveling 30 degrees north of east with a velocity of 25 meters per second. If there is an eastward current of 10 meters per second, what is the resultant vector of the boat's motion? So this is a little bit trickier. So first we're going to draw a picture. The issue with this example is we have two different velocity vectors that are occurring in two different directions, but one of them is already at an angle, so they're not going to be perfectly perpendicular. So if the first angle is 30 degrees north of east, this is actually our velocity vector of 25 meters, and this is our 30 degree angle. Our second vector is 10 meters per second completely east. So notice this red arrow and this green arrow, we can't just Pythag because they're not perpendicular to each other, but we can combine them still. So the red arrow I'm going to separate out into two different vectors. Blue is the adjacent leg, and yellow is the opposite leg. And I want to solve for those two different values. So I'm going to be using trig. We have SOHCAHTOA. I have the hypotenuse value of 25, so I'm going to use sine to solve for the opposite leg, this yellow one, and I'm going to use cosine to solve for the blue one. So sine 30, because that's our angle, is opposite, which we don't know, over hypotenuse, which is 25. So in order to solve for that opposite leg, or that yellow leg, I'm going to multiply these two numbers together. And our opposite leg is 12.5 meters per second. We're going to do the same thing for the adjacent leg. Cosine 30 equals adjacent over 25. I want to get the adjacent by itself, so I'm going to multiply those together. And the adjacent leg is 21.6 meters per second. So now I'm going to go up here and I'm going to add that to the diagram. 21.6 and 12.5. and I'm going to redraw the diagram. So we have a blue arrow going to the right. That's 21.6. We have a green arrow that is going to the right. That is 10 meters per second. And then we have a yellow arrow going up that is 12.5. So now I want to solve for this leg of the triangle by adding them together, and then I can do Pythag. So 21.6 and 10 in the same direction, that is the same as 31.6 in this direction, and then 12.5 going up, we want to solve for this line. So a squared plus b squared equals c squared, 31.6 squared plus 12.5 squared equals c squared. 31.6 squared is 998.56. 12.5 squared is 156.25. When we add those together, we get 1,154.81 equals c squared, and c equals 33.98 meters per second. So with that northeast velocity and the eastward current, instead of just traveling the 25 meters per second that we set out to travel, we're really traveling 33 meters per second. So now we have to solve for the direction and the angle. So again, we're going to use tan theta equals opposite over adjacent, and tan theta equals 12.5 over 31.6. Tan theta equals 0.395, and then inverse tan both sides to get rid of that tangent, and inverse tangent 0.395. So inverse tangent of 0.395 equals 21.5 degrees. So we are traveling 33.98 meters per second at 21.5 degrees north of east, because that's this angle right here. Okay, so this is a more involved example. I expect you to do the previous ones in class tomorrow, and we'll talk about how we're going to take it a step further to get to one like this. All right, see you in class so we can practice.